this is the Compiler Explorer talk. As you probably noticed, there are some other cool talks that unfortunately I'm having to miss by being on stage here talking to you. So I appreciate that you're here listening to me. So obviously we're talking about Compiler Explorer here. I always wanted a little quick bit of history about how we got to where we are right now. At the end, I've got a little bit more in-depth, and depending on how much time we've got and how interested people are, I can just talk forever about how this complicated piece of software works. So Compiler Explorer started off looking like this. So this is in 2012, so we've been going quite a long while now. It was an internal project that I kind of hacked together at the company I was working at, which is DRW, a finance trading company in Chicago. And I was having an argument with my boss. And, you know, so to give him his credit, we had just come out of writing some Java code where iterating over a container using the sort of range for equivalent in Java is more expensive than doing the int I equals 0, I is less than the size of it, because every time you do this, it creates some iterator object, and that creates garbage, and eventually it slows it down. So when I sort of said to him, can we use C++ range fors, he was like, no, it's probably slower. And so I said to him, I'm sure it's exactly the same, honestly. And he said, well, write some benchmarks. We looked at benchmarks that were roughly the same. But he's like, no, I don't know about it. It doesn't seem right to me. There's got to be something going on. So I wrote a little shell script to run the compiler in a loop, and I split the terminal in half, and I left that running on one side, and I had VI on the other, and we went back and forward, toggling backwards and forwards between the two different approaches. And we were looking at the assembly output, and we were like, oh, it's actually one instruction fewer to do it the new way. That's cool. And we thought, this is kind of handy, this kind of thing. And a friend of mine had just shown me, little knowledge is a dangerous thing, right? Had just shown me how to hack together a little web app. And this is the result of it. I put it all together, and we had this first version, which you'll notice is, you know, vaguely similar to what we have, but a little basic. So you'll notice that I'm not good at naming things. Look at the original name of the site at the top left-hand corner. It's called Interactive Compiler. I hosted it at gcc.mypersonaldomain because it was really, I thought it was more like a GCC Explorer. And I never thought twice about that. You know, I had my godbolt.org domain. It's still where my email address is. It's still where all my other projects, well, until very recently, where all my other projects are hosted. But obviously, I think most of you looked at the domain name and went, oh, that's what it's called. But as you know, it's called Compiler Explorer, or GC Explorer as it was then. So in 2012, we had GCC and Clang, which means that even my name then, GCC Explorer, was wrong. We only did C++, it was unfiltered, it was about 5,000 lines of Node, and it was just me, and I funded it myself. I had a question before we even started saying, do I pay for it for myself? I did originally, and it wasn't very much because cloud computing is relatively commodity these days. Today, now, we've got more than 5,000 compilers, 80 languages, all sorts of filters, tools, and diffs, which I'm going to talk about shortly, which is why you're all here. We've got 120,000 lines of TypeScript somehow. There's an amazing team that helped me support it, and we have patrons and sponsors that keep the site going, which is just as well because it's like another mortgage payment. This is what the compilations look like. No, we haven't suddenly stopped doing lots of compilations. I changed the way that we record data, and I didn't realize it until much later on. So we've lost the data from about the beginning of 2025, or it was tapering off. But you can see this is the number of monthly compiles we were doing. The tail off in the sort of end of 2024, where we dropped from like 18 million peak down to 12 million peak, isn't just like Christmas and holiday times, actually. It was a one-line change in our code base, which changed the default time between you finishing typing and the compiler like firing up anyway. We just made it 3 seconds, I think, rather than the 2 seconds that it was before. And that was enough to bring down the type. And I'll show you how to change that if you are clapping in the front because you don't like it. Nowadays, our stats are more online. You can go and actually look at our live stats dashboard now at stats.compilerexplorer.com. You can see how many machines we have running, the number of compiles we've done this week. This is a fairly typical week. This screenshot, I think it was 2 weeks ago. So lots of things going on in the background. People ask me this. It costs about $3,500 a month. Now this is a little bit out of date even, because I'll tell you in a second. But yeah, but three or $4,000 a month. That works out as 0.039 cents per compilation, which is a pretty good cost. That's pretty good bang for buck. That bill is split mostly in AWS fees and in about $500 in other bits and pieces, like buying licenses for software and like other external monitoring tools and stuff. And I've got a huge blog post that goes into all this detail at my blog at xania.org. Most recently, we have had AWS themselves have given us a grant, an open source grant, and have given us a decent chunk of vouchers, coupon, whatever they're called, credits, thank you, in the front, credits that cover a lot of the cost of it. So that's a fantastic thing. That means I'm just saving more money for when they inevitably don't let me renew it in a year's time. So we're in a good spot, though. We're in a good spot. Okay, enough of the background. Let's start by me realizing that in this split screen display that I'm in, I can see my speaker notes just fine, but I can't see the screen that I'm about to try and use. So we're going to see how well this goes. We move the mouse pointer over here, and it may be you see a little bit behind the curtain. Yeah, this is not going to work. 1 second. Let me change this to be mirrored displays. Using the power of the function key and mirror, and hoping that this doesn't upset all the recording. Okay, and now you can see that my son has an MRI right now. That's useful for you to know. Okay, he broke his knee. Poor guy. All right, that is too big. Stop it. Stop it. Okay, here we are. This is the UI we know and maybe love. I don't know. It's a kind of the UI that only a mother can love, right? It's kind of grown organically. I'm no expert at this. It's definitely been like, people add a load of stuff onto it. It's a bit of the Homer Simpson car, if you think about it. Everyone kind of bolts on the next thing that they want. We don't really think too hard about whether it's a good idea or not. So the things, luckily I have this very low-tech way of showing. Things that you see up here, obviously, is the left-hand side is the code, and the right-hand side is the assembly. I'm sure you've all worked out that the coloring matches as best we can between the left-hand side and the right-hand side, and that mousing over the various sections highlights the corresponding section on the other side. And that if you don't really know what an instruction is, you can mouse over it and you can get more information. You can also right-click on it and go to more documentation that tells you more. We have support now for ARM and I think RISC-V, but it's a little bit out of date. The other things that are worth noting on this page is the fact that there are these other buttons over here, which because of the zoom, unfortunately, aren't showing you their names. Like, this is how you'd probably normally see them, with this add new and add tool thing here. This is a sort of anachronistic thing. There is a distinction in the code base about 2 different ways of adding things to the results of your compilation, and because we're terrible programmers, we expose them to you directly as UI elements rather than just hiding and papering over the whole thing. So sorry about that. But you can add a new like whole pane. Now the sort of distinction between these 2 things, the add new generates a new pane, and that is typically something where we have to inject ourselves into the compilation itself. So for example, one of the things I'll show later on is stack usage. That means that we're going to be putting in a whole bunch of flags to the compiler and then parsing some auxiliary output file that it generates and then showing a view from it. So we kind of have to know about those ahead of time, which is why they're in this particular drop-down. This second drop-down over here, add tool, these are sort of post-compilation tooling. These are things that, having done the successful compile, now we're going to run something like readelf or PA whole or some of these things that look at the binary output. So that's the distinction between those 2, and I'll show some of them off in a minute, but I just wanted to explain why they're, basically apologize why they're the way that they are. When you are generating these drop downs, so like, if I want to add a new compiler, I notice a lot of people click them because that would be like a normal UI thing to do, right? You go for the drop down, you click the menu item, and something happens. So if I click a new compiler here, it does indeed pop up a new compiler. And now I think, well, I don't really want the compiler over there. I can go and drag it. Now, all of these things are very draggable, so you can move them anywhere you like. So you can put it over here or whatever. You can even stack them so that they're in like a little tab mode up here, because if you don't get enough tabs in your Chrome tabs, you can have tabs inside your tabs, right? So that you can tab while you tab. But what you can do, and this is, I forget that other people don't know you do this because it's the only way that I do it, is you can actually click and just drag off of that, and then you can just put it exactly where you want it. You don't have to kind of click and then go hunting for wherever it appeared and then land it in the right place. While we are here, you can also rename these things. So if you're actually kind of opening up multiple views, one's got optimization on, one's got optimization off, and you can't remember which one's which, you can give it a new name here. You could say this one's called Bob, and then if I make a new one of these, I can clone this compiler. So this will give me exactly the same settings so that I can go into a second one, and then maybe I can make this one, Clang x86, which I'll come back to in a second. And then I can rename this one Ian because that's a sensible name for these things. But now I've got like useful names for these particular things. You can also maximize them. So if you're, for example, in a demonstration where you're on stage talking to a bunch of people, and then you've got a tiny little window that pops up, then you can actually maximize it to make it take up your limited screen real estate, and then you can at least just talk about one pane. And then you can, confusingly, this thing that looks like it's minimizing it actually just restores it back to however it was before. Or not. There you go. Or not. There we are. Thankfully, it did do that. And again, you can see that it's not doing very well on this smaller screen where I'm zooming it a little bit. I wonder if I unzoom it one more. Is it still readable-ish? I'm really trying my best to kind of toe the line between getting stuff on the screen. Yeah, I'm getting a thumbs up from some people at the back there. So yeah, you've got better eyes than me. I think Herb and I are in the same boat when it comes to not being able to see very well. Yes, compiler selection. This is something you do a lot, I imagine, right? You may have noticed that we have quite a few compilers, and that can be sort of a blessing and a curse. So obviously, this drop-down is, not necessarily the most easy thing to go hunting for your exact one. But you can see, you can favorite them. You can if you find one you like, you can tap this little thing here, and now it appears as a favorite at the top. And so if you've just got Clang and GCC trunk, you can mark them as both as favorites, and then that you can find them a little bit easier. This text box, I've discovered most people don't realize, is kind of a really fuzzy FZF kind of type text box, if you know what that is. It's a fuzzy find. So I will do something like just type Clang x86, and now I've got all the Clang x86 builds, and then I don't want all of those versions, so then I just type trunk. And now I've got Clang 86, trunk, and you can put them in any order as I've kind of done here, and then you can select it and get it from the list like that. So that's pretty cool. But you can also just pop out this massive dialog box here, which gives you different ways of filtering by instruction set, by category, by search box as well, and then you can sort of favorite them here and un- and defavorite them, and you can see how many stupid compilers we've got. It's a nightmare. Yes, compiler. Oh, settings. Yes, we have settings. Settings are useful. We store all of this in local settings, browser local settings. So they should persist. If you come into a different Compiler Explorer domain, you might not get the same settings. So for example, if you click a godbolt.org link, you'll get the godbolt.org sort of local settings. But if you go to compilerexplorer.com, you get those compilerexplorer.com ones. And there's a natty trick for later that I'll get to at the end that you can use if you need two sets of options, for example, other than just using godbolt.org for one and Compiler Explorer for the other. So in the settings, there's any number of things. You can change your site theme. I've chosen light here because it would, it seems to be better on these projectors, but obviously I'm not a monster. I'd normally be in dark mode here. We have various different rainbow highlighting schemes that you can pick from here, two of which we attempt our best to be colorblind safe for those. You can configure the default language. You can do all of these various things here. By default, for example, we will temporarily store your source code if there's an error on our servers. We will delete it afterwards. You can untick this and we'll never see it, other than it's stored briefly on the disk. I spent an awful lot of time writing the privacy policy for this because I really wanted to be super, super transparent about what we do with your data. I don't read your code. I don't care about your code. I never want to care about your code. But obviously you put code into it and you trust us with that. So I just want to be clear that we do our level best to make it not available generally, other than if you choose to share it yourself. But I got fan mail for the privacy policy. I was pleased about that. Someone said how great it was. So anyway. Compilers, the setting that I wanted to show, because Lara was talking about this, is if you go to compilation, the default obviously is the classic Compiler Explorer experience of you type and it points out all the mistakes before you finish typing and you get annoyed with it and you get annoyed with it. But you can turn that off. You can turn it off and now it won't compile until I tell it to. But where's the fun in that? If you do want to tweak it, you can disable our automatic delay, and then you can fiddle around with the settings here if you like to be turbo quick. There's some other settings that you can do here as well. You can play around with those, obviously. And also on this more drop down up here is the thing that I use the most, which is reset code and UI layout. Because when I've inevitably clicked someone else's link and it's left remembering all their weird configuration, I just want a clean slate. And that's what I do more often than not, just to get it back into a good state. What else have we got on the general page here? Okay, other things you probably never knew about. This is what the whole talk is. The little green icon here obviously is it compiled okay, and I say obviously tongue in cheek, but if I break the compile in some way, if I just put like a 6 in the middle of the code there, that will go red and tell me that there's a problem. It'll also go amber if there are output from the compiler like a warning or something like that. It's not very clever at noticing if it's a warning or just some output thing, and MSVC just loves to print the name of every file every time, just because it's proud that it's working on something. And just don't tell me. I know you're compiling because I told you to compile. And so it tends to show that up anyway. But there is a sort of hidden cheat code to it. If you mouse over it, if you click it, it used to be mouse over. If you click it, we actually show you the actual command line arguments we sent to the compiler, because we do fiddle with those command line arguments if just to generate the like stack traces and things that if you've enabled in the views. But if you want to like report a bug to GCC or Clang or whatever, it's useful to be able to tell them exactly what we sent to the compiler. So we make them available here in this incredibly user-friendly and discoverable way. Beg pardon? You can. Oh, yes, you can definitely select it. So you can copy paste that into your favorite place to report bugs. Let me put this back. Oh yeah, while we're here, oh gosh, there's so many things, and maybe I'll be doing these out of order. You'll see. But the information is flowing. That's the main thing. This massive list of command line options over here are the ones that I typically run with. Wall, Wextra, Wera, standard. They get unwieldy after a while, especially if you're copying them out of like your own CMake. If you're trying to replicate something you're seeing in your own compiler in your own projects, you end up pasting 400 miles of like various random ass command line flags. And it's a pain in this tiny little box, so you can in fact click this little drop down and open the detailed compiler view, and now you can edit it like a text document, and you can add all your flags in that spot there. So that's somewhat useful. I hope that is the right close button. It is. Phew. Yes. Okay. Now, so this is another cool trick. I'm just going to put optimization on. Let's do 01 on that one, and then I'm going to make a new compiler down here, and I'm going to change this one to be GCC trunk, or trunk. Live demos, everyone. Not ARM. ARM's lovely, but not now. GCC, there we are. Okay, and of course it doesn't default. I forgot. I have a local hack for presentations where it makes it bigger font by default. Anyway, so we can run the same code through two different compilers, and sometimes it's useful to look at the difference between those. So one of the things you can do is add a diff view here at the top. I'm going to put it over here and then maximize it, or attempt to, but I can't because it's... There we are, you can maximize it. And it used to be the case that it would choose two different things to diff instead of the same thing twice, because that's not very helpful, but somehow we've got a bug. Here you've got a difference view that lets you kind of hone in, and obviously the nature of assembly is that very often the differences, once they start, are massive, and the whole thing looks different, and this is just a wall of red and green, and you don't really see it. But occasionally it's useful to kind of compare and contrast and say, oh, that's interesting. I wonder why Clang prefers to put the IMAL after the MOV, and GCC prefers to do the IMAL and then move afterwards. Who knows? But this is a way of resurfacing some of those ideas. And certainly if you've got like a way of like pound defining something on and off, you can compile the code once with -d, my thing, and -d, and then one without -d, and then you can compare two implementations where it may show you useful differences inside of your code. Okay, and one other thing is that if you find yourself opening up lots of assembly views like this, and you don't really care about the assembly, all you care about is does this compile or not, then have I got the view for you? We can add, oops, wrong one, off of this one here, you can see it. The UI is not confusing at all, it doesn't confuse me, I don't know what you're talking about. This is a conformance view, and I'm actually going to close off these two things here. So now all we've got is the source code and an empty pane where I can add as many compilers up to, I think, 10. So let's just have a GCC, yeah, ARM GCC, 32-bit, why not? ARM, that one, I should have really thought. But you get the idea that I can pick a number of compilers here, and the green tick is telling me that it compiled without any errors at all. And if I pick some ancient version of Clang, oh my God, I can't believe they all worked. That was not supposed to happen. But you can now change your code, and if I include some like vector up here, I bet you one of them will now break because I bet you it doesn't have vector because it's too old. Oh, damn you. Well, I think you understand what code that doesn't compile looks like. And if it did, you'd see this would be red, and then you could actually click this little button over here, and it would open up the pane again. And then you could go and look at the error, you can look at the output, you can understand what the heck's going on with it. But if you're sort of doing some gnarly template stuff and you're not sure what 3 or 4 compilers that you have to support it, you can use that. And then last of all, in this part, there's this big templates thing at the top here, because I love templates, as you know. They're a thing that I enjoy. These are not C++ templates. These are templates for the website. And we have some pre-canned sort of setup views, because it can be awkward to set the code up and move all the windows around and all that stuff. So we have, a difference of 2 sources, a difference of 2 compilers, a sort of simple CMake project. You saw Herb demonstrating that this morning, and actually I sent a screenshot of it to the Compiler Explorer Discord, to the other people who work on the project, and everyone was so impressed that he managed to get it set up that way, because we have difficulty doing it. I'll show you how to do it in a moment. And various other IDE modes, like, if you've ever wanted a Java IDE before in a web browser, today is your lucky day. But you can also save your own local ones as a state, so you could say this is, Java 2 or whatever, I don't know. We don't take the screenshot, we don't have that coolness, but you can kind of save it locally again. This all, again, lives in your local browser state, so it is exactly as volatile as your local browser state. So, don't put anything too precious in here. My recommendation to you is, if you've got like your one perfect setup that you love, make a short link and then save that somewhere safe. Put it in the readme.md or whatever. And probably the most frequently asked question I get is, how long can we rely on those short links living? And it is my sort of personal goal to make sure that lives forever. So you should be able to keep relying on them. We have a lot of them, and it's not trivial to keep them all working all the time, but we do try very hard. We consider it like a really high priority bug if you have an old link that stops working. Cool, all right, that is the first part. That's just the UI overview. And now, if I can go back, of course, I've done 300 different moves here. Let's go back to, there we are, oh, good. All right, we are back in sync. Next. Let's look at some tools perhaps you haven't seen before. So this, obviously, if you can read it, the green, unfortunately, the hash defined thing is a bit vague to see, but hopefully all of you are like recoiling in horror at seeing this particular piece of code. That's obviously on purpose. So here it is. Please don't use Preprocessor. I don't care about this view. You can go over there. What I'm going to, you can't go over there because I need you, sorry. I'm going to add a tool view over here from the correct menu, which is this one. And I'm going to add a preprocessor view. And so this view shows me the code after the preprocessor has seen it with some clever filtering. And so if you have some gnarly preprocessor stuff, and you shouldn't, but if you do, because we're all practical engineers and we all actually have to deal with real world situations, right? This view can help you. We've filtered out here all of the sort of the nonsense. You can take that out and it will show you all of the nonsense that gets put in there. But you can see a little bit more clearly now that this is not going to work very well for us. And that's one of the views that we have. And the next one is another page. So another view here, this is like my silly way. This is adding the numbers 1 through 82 or 83. There's bound to be an off by 1 error, and someone will no doubt put their hand up or tell me in the comments which one it is. But this is a terrible way to do a sum over numbers. And you can see I'm making an array of that size. I'm using std iota, and I'm using std ranges fold left first, because that's, I don't know, I was just playing with things. And the compiler has done a good job. It has generated a ton of code, and it's not got optimization on or anything like that. But it's doing what I asked it to do, which is fine. That's okay. But the astute among you will have noticed that this is, well, A, terrible, but B, there's a ton of stack there. An unsigned value times, it's 4 bytes times 82. That's not a trivial sized object. I shouldn't really be putting things like that on the stack. One of our other views is to actually take a look at that. We've got a stack usage view here, and it's a little confusing. Again, we're sort of at the mercy of what the compilers tell us. I've kind of made a small career out of showcasing other people's work and trying to pass it off as my own, which is what this is all about. But somewhere buried in those yellow bars that made more sense when I did this in the dry run-through, so I must have changed something, is telling us a little bit about what kind of static allocation it's having to do on the stack. Unfortunately, it's not as clear as I thought it was going to be, so I apologize about that. But one of the interesting things here is that if we do actually turn the optimizer on, I can't just leave it at that. GCC turns it into a loop without some stack usage. And in fact, if I bring the stack usage thing back up again, let's put it down there. I think now, yeah, it is still on the stack. All right, let's try 03. Eventually, it's clever enough, I think, to work out it doesn't even need to the stack in the first place. Yes, okay. So by 03, GCC has worked out that it can, in fact, just work out the answer, which is 3,403, apparently. And that's, it still looks more complicated. It's doing something else there, isn't it? It's clearly doing something else, because it should just be able to do mov racks, command, whatever. Let's go to Clang. Clang's usually smarter than this. x86, boom, whoops. Yeah, so there, Clang goes, yeah, I just know the answer to this, 82, whatever, it goes down to 0, there's that. But interestingly, in order to do that, Clang has obviously had to sort of single step through and at some point, go, all right, this does finish. It's not solved the halting problem here. And we've kind of done our best to hide away what we're doing through all these range things. And so if I put this to 83, then Clang does a great job of vectorizing the summation loop down here. But ultimately, it still could just give me the darn answer at the end. But there are limitations here. I know that's not really what that view is all about, but so Clang does give up. 0102, yes, that's right. Okay, and then we've got some other tools. So these are the tools that we can run on the binary after it's been compiled. So we've got a hello CppCon thing over here. I can bring up, for example, things like nm, which is the Unix tool. Oh, it needs a binary object. It does. Let's give it one. Let us compile to binary object. And so nm tells me the symbols that the Unix system needs to, or is either provided by or required by the object file that I've just built. You can see T means that it's expecting, it's defining main, and then U is it's undefined and it's expecting the outside world to provide puts to it. And then actually something else I didn't think to even put in my notes, but if you compile to compile to an executable, like if you link to binary or if you tick execute the code, then we actually do a full link and you get a binary, like an a.out kind of thing that we can run tools on. But if you just click compile to binary object, then we actually leave it as a .o file. And the interesting thing about .o files is they're not fully linked, but we can still look into them. And something we added fairly recently was parsing the relocation tables that tell the linker what to do. So while you're here, you can see it's saying the opcode here says call main plus .xe, right? Which is, if you look at the opcodes, it's B8000000. It's very unlikely that it's calling a function at 0. That doesn't seem right. But this R x86-64 PLT32 puts minus 0.4 is a directive to the linker that says, hey, once you found that put symbol, to link this, you need to take the value of whatever puts is, subtract 4 from it, and write it here, please. Address A. So that's how the instruction code, actually the machine code gets patched to do the actual linking. So you get to play around with that stuff too. What other tools we've got? We've got like strings, we've got readelf. So I have spent a lot of my career trying to work out why weird things aren't working. They're usually to do with dynamic linking or whatever. So readelf-d, we can go and have a look at all the different, there is no dynamic section. Of course there isn't because I didn't actually compile it as that. There's a number of like headers and things that you can go and look at here. And it's kind of a useful thing. I know that certain universities use this when they want to just demonstrate quickly, this is what happens to your executable without having to then tell everyone how to use the command line. That kind of good stuff. Okay, what else have we got? Overrides and flags. Okay, this is my favorite little example of how clever compilers are, which is just my way of sneaking it in and getting it to show to you again. So this function, which is a little bit, I didn't give you enough time to read, is count how many 1 bits there are in the input, which is a surprisingly useful thing to do. And it does it by starting with 0 and then saying while there are bits left, there is at least 1, clear the bottom set bit, which is that num and equals num minus 1, which is one of those like leet hacker tricks that you learn. It's fun to sit down with a piece of paper and actually work through it. And I don't know if Jason's got it in his little puzzle book, but that as a kind of like, why does that work is a fun little thing just to sit when you're on the plane home, perhaps. It's just doodle them in binary and work it out. But anyway, we keep doing this in a while loop, and GCC over here on the other side, which is not running any optimization at all, does exactly what we asked it to, and there's a loop and everything, and that's fantastic. But most things these days will generate better code. Oh, except it didn't. So I was expecting it to generate an instruction that can do this in one go. But I haven't told it that it can, because at the moment it's currently targeting a processor that doesn't have that instruction. I know that there is an instruction that does that, but I can never remember what the darn flags are for all of those things. So we have a tool for you, this overrides button here. We have a limited number of things that we know are awkward, and we can read out of the --help or the --help --extra or whatever it is in the various compilers. And so architecture is one of those things. So we can actually parse out all the supported architectures for the current compiler, and then you can sort of scroll through like a history lesson of all the different things that Intel have put out over the years, and their strange fetish with lakes and trails near around where they, I don't know. Like Raptor Lake though does sound very cool. I'm picking Raptor Lake. We also allow you to pick the standard version so that this will be a list of all, and unfortunately for the scaling, it's gone off the bottom of the screen here, and that's a bug on our side. But you can see all the different versions of the supported standard that this compiler reported it supports, so you can pick from there. And then essentially we just insert that behind the scenes. The little overrides thing goes on and goes orange. Gosh, green, I can do colors. It goes green to show that there is something set that's sort of slightly hidden from you. You noticed as well, you can put in environment variables. That doesn't affect many C++ compilers because they're sane and rational and they're controlled by command line switches, but things like Rust and other compilers, sometimes you communicate through them by setting environment variables, so that's a way to get those injected in. And now we can see that it has done the pop count, but really confusingly has also done all the rest of it, so I don't know what's going on here. This was not supposed to happen. Let's just turn the optimizer up to 10. There we go. That's what we were hoping for, that very cleverly it has been able to determine what, that this entire loop is just one instruction. And in fact, that's interesting. So you notice it's just doing pop count racks, RDI, so it's saying count the number of set bits in RDI, the first parameter, and put the result in racks. That's what you would expect to see. That's what Clang has always done. But what I'm used to seeing, and because I've picked Raptor Lake, because I like to go off script and confuse everybody or myself, let's pick Skylake. Okay, so this is an earlier revision of the chip. Oh, look at that. Ah, anyone know why it's decided to do essentially EAX equals 0 and then write over it? And I can see Eduardo. Is that Eduardo there, or my eyesight's failing me? Yes, yes. Do you want to shout it out?
Yes, that supposedly you had to make sure that EAX was not a dependency. So by clearing it out, it isn't.
Exactly. So there was a bug in the chip. So the chip tracks dependencies between all of the various calculations that are going on. And it erroneously thinks that pop count still depends on the previous value of whatever racks was, which meant if you'd just done a divide into the racks register, it would wait for the divide to finish before it then did a pop count to put into it, which is like, no, you don't need it. Just stop it. And XOR EAX, it knows that that's like the beginning of a new lifetime of values. So they fixed it, apparently, and the compilers know which revisions affected and which ones were not. I mean, yeah, thank you, Eduardo. Have I done all the things I needed to do with this? Let me just quickly look. Oh, yes, opt view. That's an important one. All right, I'm going to switch to Clang now. Clang, x86 trunk. Compilation failed. Oh, that's nice. That's probably because it doesn't support that target architecture. Let's pick something else. Let's pick the no architecture and hope that that works. Or else... Phew, okay, we're back. All right, I'm just gonna actually type in the thing because Clang actually supports more than just x86, so that architecture includes like everything you've ever heard of in your life. Skylake. Come on. There we go. All right, okay, apparently Clang knows that too. Clang used to be a bit funny about the XOR EX thing again as well. Anyway, so we've got a pop count. Now, if like me, you're kind of like, how does it pull off this magic trick? I've written some just straight line code in a loop, and somehow it's gone, I know that loop's an instruction. I've got a view for you. So one of my favorite tools is the LLVM opt pipeline. So I'm going to pull this out and then maximize it, and then I'm going to go and set the font size to Maybe that. Okay, it's hopefully just about readable. It's not ideal. What you're looking at here is the LLVM internal representation of the compiler as it processes your code. On the left-hand side, we've got each of the many passes that the compiler goes through to optimize the code. And the key here is that every time one of these passes run, we look at the intermediate representation both before and after that pass. And if they change, we highlight it in green, which does show up on the projector. So srow pass, that's the official pronunciation. Srow pass, no, that's scalar replacement of aggregates, I think. That made a change, and I can click on it and I can go and see this huge and complicated set of changes that happened here. And if I knew more about how compilers work really, I might be able to explain it to you, but I just happen to know, because I've played around with this enough, that eventually I scroll down here and we have a look at all this kind of loop idiom recognition passes, induction blah, blah, blah. And we get to this one called loop deletion pass. And we look at the before, and it has all this loop nonsense, and we look at the after, and there is some loop nonsense around, but it has in fact now changed all of that loop to be one call to LLVM.CTPOP.I64, which is its sort of internal function that represents an instruction that it knows that the architecture will have. So that is when this LLVM's count pop appears for the first time. And you can now just take loop deletion pass and put it into your favorite web search engine, and you will find the code for this, and you'll see some of the clever little tricks they do for like discovering things that they think are loops that can be deleted and replaced with instructions, or replaced with, like rep stosb and things like that. So it's super cool. So it's a little window in, and I wish I knew more about compilers, but I do not. Which everyone seems to think, oh, you must know loads of things about compilers. I know how to run compilers, like nobody's business, but I have no idea what they're doing inside. They're just magical boxes. Okay, we have execution. We have execution, which I'm sure most of you know about now. It's not the most discoverable feature. There's a theme. So here it is. I've got this, little puts for every argument that you pass on the command line by using spans and clever things like that I thought was clever at the time, but now doesn't fit on the slide. And we've got the code on the right-hand side. And many of you know that you can change the mode over here and say, execute the code. And then, now we're doing loads of resources on our side. We're running your code, but you're not even looking at the output for it because, you have to now open the output window. So this is just an absolutely terrible design. But nevertheless, our program returned, and it said greetings to output.s, because of course argv0 is the name of the program. So yeah, we output.s. You can see how bad this is, right? So when we originally started this, obviously the whole thing was just about the .s file. And then as things have ticked on, we've never bothered to rename it. So it's still called output.s, even though it's a binary and we're running it. So it's there, but I'd like to be able to actually put in some command line arguments. And at this point, it was starting to get, even for my taste, too complicated in this view. And so we actually have a completely different view that you can do much more fine-grained execution work with. So one of the things you can do is you can add an execution-only view down here, and I could drag that off and then I could sort of set it up much in the same way as the compiler. Or if you already have a compiler and you're like, well, I just want this, but I want it to be the execute view, you can use this add new and do executor from this, and then you can drag it and put it wherever you like, and I'm actually going to drag it and sort of stack it up here so that we only see one of them at a time. It's still doing both of them, and now, but I could just close the other one. We're not going to look at it again. Okay. So now we've got the same compiler, the same arguments, the same everything that we had before, except that all we're really caring about now is the program and its execution, and we've got more options. We can still add libraries, we can still run some overrides. I can actually tick this down and I can put in arguments here, so like CppCon. So now it'll be greetings to CppCon, and then monkeys in, why have I put quotes? Because I know it's not going to work. In a cage. Is that going to work? Oh, it did. Who knew? I didn't know that I'd implemented this properly. Sometimes I surprise myself. Okay, so you can add your command line flags here, which is, command line arguments here. You can also include standard in. So I can open this up and I can paste a document in. So if you want to actually run the input into the compiler and use std c in and other horrible things, you're welcome to. Another cool thing, though, is that we've got some things over here. We can enable Heaptrack, so we can link dynamically against Heaptrack, which checks how many allocations you're making and when they were made, and we parse the output of that and we can present it to you. And this is probably the most useful one if you're trying to teach people how C++ works, and if my mouse would work. There we are. We can enable libsegfault, and so libsegfault catches segv and prints a stack trace. So, if I do everyone's favorite little bit of gymnastics over here. Do I have to put volatile these days? I mean, it's more correct, right? Please work. And crash. There we go. So we've now got an almost unreadable because of the colors stack trace, and then you've got at least some hope of working out what happens there. Checks notes, libsegfault. Oh yeah, we don't have to just do x86. Nowadays, we can also do this on ARM. Let me get rid of this and then get rid of that. Oops, if I can actually... Now, normally I don't do this in this mode, so I'm going to turn off the libsegfault because otherwise I will expose the fact that it probably doesn't work. ARM64, GCC trunk. Unknown Skylake, yes, that is not a valid architecture for ARM. This is where we have to wait a little bit longer. SIG-bus, well, that's exactly what, I think actually that's a known bug. I think someone in the front row is probably going, don't do that. Let me just try GCC 15.2. We're in the middle of throes of operating system changing. There we go, phew. All right, something works. So ARM64 trunk doesn't work, but ARM64 15.2 GCC does, so we're good on that front. And if I could think of something that could show you, prove to you that it is actually running on an ARM-based computer in like a short amount of time, I would. But this is kind of a heavy lift on our side. Our infrastructure is all x86 nodes, and then suddenly we were like, well, it would be really cool. And we've tried emulation and things like that, but the thing about emulators is that they tend to want to do cool and interesting things like hook into the operating system and do stuff to make themselves run faster. But we're already in a sandbox in a VM, and there's only so many layers of turtles you can have before the whole thing starts falling apart. I mean, I think QEMU in the right mode might work for us. We could emulate it, but we're actually just running on an actual ARM machine. So you have access to ARM machines, and we're in the process of making that even better to add more things, which reminds me, we can run on a GPU. The single most expensive thing that Compiler Explorer does is have 2 GPU nodes up all of the time. I don't know very much about GPUs, other than with enough copy pasting, I was able to get this to work, and by work I mean compile and then print out a number. So this is actually, currently, this is building on a GPU instance. And the interesting thing when you start building GPU-based stuff is that you get 2 parts of the output code. So this second window on the far right with the tiny writing is automatically popped up when it detected that we'd built an image that contained more than one ISA. So this second ISA here means that this is the code that would run on the x86 host. This is the code that runs on the GPU. That's kind of how this stuff works. And there are 2, this is more, I'm way above my pay grade here in terms of talking about what on earth this is all about, but the way that I understand it is that PTX is sort of the intermediate representation that the NVIDIA GPUs use, and this may only be NVIDIA, and then it gets optimized down to a particular specific architecture so that you can kind of ship it to across heterogeneous different types of GPUs and have it still mostly work without having to rebuild for every single GPU. So you can look at both of them here. But you can also run it. He says, please run, execute the code, and get the output window up. And wait in a queue. Your compilation is important to us. There we are. Maximum error is apparent. Whatever example I picked up has a maximum error of 0.000. Very exciting and interesting. I'm glad you all waited with me for that. It's possibly the most expensive compilation we've done yet, but there it is. So we've got GPUs. That was another big lift to get another sort of cluster of machines that run GPU full code. And yeah, so analysis tools. Now we're into the meat of this stuff. This is good stuff. And I've only got 16 minutes left. Blast. Okay. This is a little bit of code that just sums the squares of numbers. And of course, there are much, much better ways of doing this for all the reasons, but I've decided to write it that way. So it sums up the squares and returns them as a float. And on the right-hand side, if you know a thing or two about parallelization, so we're using GCC 15.2, we're on 03, so it's like saying, do your best, go, 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 go. And GCC is doing... It's doing something. I mean, the way that I typically, when I teach these kinds of things, is I say, I look for the loop. So L2 is the loop here. It's annoyingly just bigger than it fits on the slide here. So I can see that JNE L2 and L2 at the top here, that's the loop. So that's my thing that's going to repeat over and over again. And then I look at how far it's moving the pointer each time round the loop. And I can see it's doing an add RDI, 16. I'm like, oh, well, floating point value is 4 bytes. and it's moving 16. And there are all these complicated looking instructions that have mulps and they're using the XMM registers and things like that. So like, therefore, it parallelized it and used SIMD instructions. Hooray, it's fast. Except if you look at, and so that works with a lot of these kind of things as a rule of thumb. It's like, has it parallelized it? Yes, it has, but we've hampered it. And we've hampered it because the rules of floating point. So what it's really doing is it's picking up 4 numbers, it's squaring those 4 numbers, and then it's serially adding them all together in the order that I've asked it to do, because floating point works that way. And so in order to keep the IEEE happy and have them not arrive at your doorstep and knocking, saying where are our bits of precision gone, you have to do it in the order that you said in the program. Okay, but I mean, many of you now, the go-to is to use my favorite and scariest flag in the compiler world. Does anyone know where I'm alluding to? Well, go on, shout it out. Fast math. Oh, that's true. That's cool, but it's not fun. It's
Unsafe math optimization.
You've pronounced it wrong, but you're correct. Yes, it's fun, safe math optimization, because they are both fun and safe. No, the command line is F unsafe math optimization. It enables a whole bunch of optimizations that are essentially, I think Chandler Carruth is quoted as saying it's like unbounded precision loss you're just basically letting yourself go into. So don't do that, generally. And F-fast math and O-fast and all these things, they do this. They enable it globally, and it's frankly terrifying that you are allowing this on your code. So my instinct is to always use a little magical thing. This is obviously a GNU extension, but Clang accepts it as well. And so I'm just going to tell it here, what it is. It is dash, oh, hang on. This is in my notes. I really should have remembered this. Wrong, how you get to see how the sausage is made here. My favorite, no, oh, God, no, I didn't write down the stupid thing in here. Can anyone remember what the flag is? It's associative math, haha, there we go. Associative math. And this is like putting -f associative math, but only for this function. And that's super useful because, you know, now I get the loop I was expecting where it's doing a smaller loop where it's summing the squares. And so we'll end up with 4 subtotals of squares. And then at the end, we just do the one sum of all the squares to get the subtotals together into one total. And I've kind of minimized the blast radius of that change, which is a nice thing to do. I'm sure someone can say, yeah, something, ODR violation, something else. So, you know, you have to be very careful with these kinds of things, but you kind of are in that world anyway, especially if you're toggling F-fast math on and off and using things that are defined in headers. Who knows what you're going to get, so just be careful. This is all a big setup because now I want to show you how cool the tooling is. Now, I can add this as a tool to Compiler Explorer, as in I can drop it down and add a tool for the thing I'm about to add. I'm not going to do that because I want to show you a subsection of it. And at the moment, we don't have a good little way for me to wrap a part of the source code and say, I'd like you to analyze this bit. But what we're going to do is we're going to analyze the code. I'm going to pick out the loop, which I've already said is the bit I care about, because that executes once for every 4 floats. That's what they're called. And now I'm going to change language over here to analysis. We've got lots of languages. You've probably noticed that. This is the OSACA, the open source architecture analyzer, but I'm going to not use that. I'm going to use LLVM MCA, which is my wrapper name. No, sorry. And this is the low-level virtual machine code analyzer. And what this does is it uses all of the tables and knowledge inside of Clang about how all the various parts of the CPU interact, and it kind of turns it into a simulator rather than a predictor. So when it's optimizing, it's trying to predict and say like, oh, if I schedule this instruction here, then it'll have to wait. Why don't I put an instruction in that doesn't have to wait? And that's while it's generating the code. But in this instance, what we're doing is we're asking it to say like, well, I have the code. Just assume that this is the inner body of a loop, concatenate it end to end 100 times, and then tell me what would happen. And so it's telling us that like for 100 iterations of a loop, that would be 600 instructions. That's fairly basic maths. It would be 413 cycles, though, which is a very unusual number of cycles, I have you agree, because of all the clever things that are going on inside the CPU. And it gives us a breakdown of all the things that are going on. But my favorite thing to do is to put dash timeline up here, and then maximize it, and then hope that we can get some kind of view here. Yeah, somewhere down here, we get this beautiful ASCII art, and one day I will make a view for this. This is one sweet day, I will do a view for this. But what we're seeing here is time going left to right, and the D means it's decoding instructions. So what we can see is in the first clock cycle, based on the current model that it's inferred from my command line flags, it thinks that the first 6 instructions will have been decoded in one cycle. And then in the second cycle, 2 of them are executing. And then down here, this one's this is the second iteration of the loop. So on the second cycle, it's already started on the second iteration of the loop because of all the clever branch prediction and register renaming and all the things I love to talk about but don't have the time to talk about now. But you can look through this and you can sort of marvel at like this feat of engineering, and you can kind of see this R is when it's retiring the instructions. That kind of pattern on the end there is effectively the throughput of the system. All those other instructions don't really count anymore because they're being executed while everything's waiting for the other instructions to finish. So it's super cool, it's super fun. It is not necessarily 100% accurate. There are better things, and I want to investigate those, and I should do because I have some free time at the moment. Yes. Oh, that was loud. Sorry, everybody. IDE mode. Yes, let's go and do that. This is the one slide where I hadn't actually prepared because I thought, I know, I'll just do it. How hard can it be? Ha ha ha. Well, you're about to see me be hoist by my own petard or whatever. Look at this. What on earth is going on? Oh, you see, this is what happened. I have gone to godbolt.org here as opposed to slides.compilerexplorer.com. So I'm letting you know the secret I was going to tell you at the end. It's like almost everything .godbolt.org or .compilerexplorer.com or actually .godbo.lt, which in a sort of fun thing I registered, anything that will go to Compiler Explorer with some very weird exceptions, which is a fun thing for you to find out. Which means that effectively, if you want a different set of flags, like for example, all the things we've been looking at have been at slides.compilerexplorer.com because then I could set the zoom in Chrome and I had all my settings. But I've just typed in godbolt.org and you can see that normally I live in pink because it's a better color. Or dark mode, honestly. All right, but I'm going to do my, whoops, wrong button. I'm going to reset code and UI layout. We're going to try and off the cuff turbo this, where I'm going to show you how to get it into IDE mode. So we start out with just the usual view. I'm going to add an IDE mode thing here, which is a tree. And this is effectively like the little pane on the left-hand side of Visual Studio Code that says, no, these are the files in my project. By default, nothing is in the project. You'll see on the left-hand side at the moment, included files is empty, excluded files has C++ source number 1. So the first thing I want to do is add this to the project and call this example.cpp. Why not? Okay, so now it's in the kind of build tree. Any build that's triggered from that IDE mode will get all of the files there uploaded into one directory before it's run, which means that you can compile multiple files, you can include header files, you can even put test data up there, and then you can even read it when your code is executing because you've got your own little jail with your files in it. A caveat here, I mean, it's unlike C++ developers to expect, a sharp edge somewhere in the process, but a sharp edge here is that this compiler that we've got over here was generated from that one editor. It's got nothing to do with that project, and so it's actually unhelpful to me. And if I included something up here, this compile would fail, because this is like me just running that on its own, that one file on its own. So I'm going to close it, because it's confusing, and instead I'm going to add a compiler that's a child of the IDE tree mode over here. And now this compiler is seeing all of those files. I can add another file. Let me just add a new source editor, and I'm going to drag it immediately up to next to C++ source there. Again, we just get the default. Have I got the right one here? Yes. And I'm going to say project test add executable. What was it? Example.cpp. And then I'm going to save this over here, and then I'm going to do that thing that we all hate, which is I'm going to rename it to be a different type of file, cmakelists.txt. What could go wrong? You can see now it knows it's a CMake file. That's great. Everything's wonderful there. I'm going to tick the box over here and tell it that the output is going to be example. Obviously, we can't tell what the name of the thing is that you're about to build is because you could type anything in CMake, so we don't know which file to open up at the end. And if we're really lucky, there's a green dot there. Seems highly unlikely that it's worked. Yeah, it doesn't look like it did work, actually. So what have I done wrong here? I don't know what I've done. Oh, no, there you are. OK, it's actually triggered now. It was just taking its own sweet, mystical time. What is our output? What have I misspelled here? OK, so CMake ran. And, oh, because there's no reference to main. Oh, that's an easy thing to fix. Hallelujah. All right, so we've got our example up here. If I had more time, what I would do is I would make another function, another file, and I would put the main in that, and then I would extern the square in the other function, and then I would show that they were linking the two of them together. And then my usual party trick after that is to go up to the flag box and turn on link time optimization and show that it can inline the square, even though it was defined in a different translation unit. But, you know, so this is complicated, it's awkward. We're software engineers, we're not UX people, but you can go over to here and click C++ CMake, and you get like a starting point that is, with a bigger screen, is a bit more understandable. This, for example, has a hello.txt file that it opens and streams through and reads and has some I/O, and so it's a decent way to like at least dip your toe in and see what kind of complex maths we've made for you. Yes? Question?
Can you do modules with that?
Can you do modules with that was the question. Yes, you can do modules with this. There are some links somewhere that are on the internet. I don't know actually where they are now. I know I've seen them, but people have used it to make modules. But it's not brilliant because we don't have anything to persist them. And so they are just slightly slower than doing it normally. But you can at least do them through the mechanisms that CMake gives you. Yeah, we have a new enough version of CMake that lets you do that. Okay. So yes, we talked about this. MISC trivia, anything.godbolt.org, nearly everything that .godbolt.org goes to Compiler Explorer, and you can use it as your own personal subdomain. For example, I use slides.compilerexplorer.com for my slides, so they keep everything separate from that. If you go to a subdomain of Compiler Explorer that happens to be a language name, it will start out by default in that language. So if you go to rust.godbolt.org or rust.compilerexplorer.com, you get Rust up by default. So that's another way of sort of partitioning things and sort of getting there quickly if you so desire. Why would anyone at the C++ conference want to do that? I know, sorry about that. And yeah, we have two other domains as well, godbolt.lt. I was so pleased with myself when I thought, oh, I wonder if I can get gdb.lt. You know, it's Lithuania, and gdb.lt is kind of small. That could be my short URL kind of version. But unfortunately, it's a church in Lithuania, and they didn't want to sell their domain. It seemed rude. So we've got these. We'll start with these. I think we've got somebody has got compilerexplorer.org and redirects to us. That's not quite the same, because the redirect means that if you go to the .org, by the time you get to us, it is the .com again, so you get those local settings for that. I did go through a period of time when I was more sensitive to everyone calling it what they call it. And so I was thinking of phasing out the first domain name up there, but I have been, you know, roundly talked off of that now because everyone likes it and it's short and knows what it is and it's a kind of cool word. So I've accepted the mantle of that now, even if I don't use it myself, so hopefully you'll forgive me. Oh gosh, 2 minutes, 41. Time goes so fast. So behind the scenes, it's a mess of so many services, and it's about to change again, actually. We've got a big, big refactoring coming. We've just finished one massive refactoring about how we store all of our compilers, which I'll talk to you forever afterwards, but I've got a blog post about. There are lots and lots of moving parts here. It has grown a ton in 13 years. It really has. And the level of sophistication is getting quite up there for a jumped up DevOps C++ programmer trying to write JavaScript, right? You know, I've got 2 minutes to talk about any of these things here. So sandboxing. Turns out, even before we had, you know, run your own code on Compiler Explorer, a compiler is a massive attack vector for somebody. There are so many command line switches that do naughty things that you might not think about it. So the best example I've got is somebody found a way to crash Clang in a way that revealed the temporary file that it had written to before we had sandboxing, right? And our usual scrubbing didn't match it. And so they would crash Clang. It had written out a .o file somewhere, and then it had given out the actual real path of it. So it was /temp/ some giant number /blah.o. And then in the second incarnation, a second request, they would load that path in as a plugin into GCC. And then they could run arbitrary code inside GCC. Now, obviously, they had to get scheduled on the same machine and had to hope that we hadn't, our directory, you know, /temp cleaner hadn't run, but that was the kind of thing we're up against. So we had to sandbox our compilers, and then by that point, we realized that we could, we were confident enough that our sandbox would keep us safe. So we started letting you run your own code. I've talked about the CEFS, AutoFS, that's like managing 4 terabytes of compilers is not trivial. I'll talk to you forever. The big change that's coming in the next few weeks is queuing. So at the moment, if you submit a request to Compiler Explorer, it hits our load balancer, and our load balancer does its best job of trying to spread the work out across our machines. but the machines then queue up the work on them. And if you unfortunately get your tiny little hello world program behind some joker that's just put 3 massive template metaprogramming tasks in front of you, then you're going to be waiting 60 seconds before those complete, and then your thing even starts. I didn't show you, but one of the buttons on the bottom is a little button you can press, and it shows you where the time was spent, how long it was in a queue, how long it was compiling, how long it was in like JavaScript code. So that queuing change will mean that we'll have a global queue, and we'll be able to like better give work to idle workers rather than you being stuck on one worker that got particularly overloaded. And so there's tons more to talk about, but I have run out of time. Thank you all for listening, and I will stay here and you can come and chat to me afterwards.